something like this. Or maybe it will just smash into the wall, and then it will smash and come back. Like when you go too fast into a curve with your car. Right? When you go too fast into a curve with your car, you have too much momentum, and so you, instead of turning around, you go straight and hit the tree. And this is what happens to this particle. So, the energy condition is necessary, but we also need to have conditions for the momentum. So unfortunately I cannot find the little example. I will show it on Monday. Sometimes you have particles and they are trapped in the potential energy well, like here, but they have so much momentum that they go long, 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 and they never find the barrier. Because they never have, to cross the barrier, the particle needs to have the correct energy, but it also needs to have the correct momentum that carries it. The velocity needs to have the correct direction.
So for example, like the first one, it needs like two different momentum in order to reach the minimal energy.
Two different one.
No. It's like they need to move like this and this, which is.
That's right. You need. I mean, here the probability to have the right momentum. So here, of course you can go like this and like this and like this, but you have. I mean, how should I say? The number of possibilities of having the correct momentum is just much, much larger. And when your reaction path, or your reaction coordinate, when this is curved, like here or here, this reduces the probability of crossing the barrier. Because the probability of having the correct energy, of course, you need that, but also the correct momentum is much lower. So sometimes you compute barrier heights, and you find something, and then you do Arrhenius, and you find that this does not agree with your experiment. This is not, maybe it's because your calculations are wrong, it can be. But maybe your calculations are just perfectly okay, but the reaction coordinate is curved. And so it's very difficult for the molecules that travel to have the correct momentum. I mean, most of the time they just bump into the wall like a car that's going too fast. And this is true in classical mechanics, but if you study in quantum mechanics, you get exactly the same effect. The wave functions show exactly the same behavior.
I have a question.
Yeah?
About the momentum. Is this the momentum of the particles?
It's the momentum of the, well, I mean, this is a very idealized view, so we don't say exactly what it is, but if you, Michael wrote somewhere, if this is A, and this is B, and what you study is the reaction or the equilibrium AB, then of course the mass of A must be the mass of B. It could be, for instance, what do chemists call it when you have isomerization? No, reorientation, when you have a molecule. When some group in a molecule.
Yeah, conformation.
A conformational change. I mean, imagine a reaction that's a conformational change. Okay? So the masses don't change, and the momentum is the momentum of this traveling mass, is the momentum that associated with the mass of A, which is the same as the mass of B. The mass does not change when you change the conformation, right? If you change the mass, then it becomes more, then people define effective masses, which means it's something that behaves like a mass, but it's not really a mass. So this view is easier to understand if you say the mass of A and the mass of B is the same, and then you can think what reactions keep the mass constant, and some conformational change would be a good example. So it could be cis-trans. I mean, something goes cis-trans. You know, this could be something cis, and this could be something trans. So, you know, molecule is like this or like this, does not change the mass. And then of course you can ask, how does the molecule look in transition state? I mean, the reactant would be like this, product would be like this. And then you ask, well, what is the transition state? How does the transition, maybe the transition state is like this, but maybe the transition state is like this, or you don't know, right? So, you know, how your molecule looks when it crosses the barrier, you don't know. But then you ask this gentleman and he will study for you.
Yeah, and what else is important or interesting in this potential energy surface? Well, we have here something at the top that is a second order saddle point. Second order saddle point.
Remove all this junk. Can you see something? It's so much stuff now.
Let's remove everything.
Let's remove
Let's come to last, yeah.
So you see what's the point.
And in our two-dimensional example, second order saddle point is just a maximum because we don't have more dimensions. So it just means that we have every direction going downhill in a multidimensional potential energy surface. It would be two directions going downhill, not just one like here. And then there is one more thing that one has often in real chemical problems, and that is that we have one more of these red curves, and that is for example this red. No, now I'm green. I make it more red. So that is this one. And that is a competing reaction. It's another reaction where the other product is formed. So here this picture does not really show the minimum, but let's assume the minimum is here. And so from the reactants you can go to product A or you can go to product B. And that's very often the situation that you have a competition. One product maybe that you want to have very much, and one product that you don't like and you don't want to have it. And the people try somehow to change the potential energy surface so that it goes more to the product that you want and less to the product that you do not want. Everybody has some examples for such a competition. For example, in your paper, I think you had the same thing. What was some product that you do not want?
ไม่ค่อยของคุณมันมีโปรดักที่คุณไม่
yeah
What is it?
ethylene
Ethylene, yeah.
ครับ is competitive อะไรนะ is competitive
with
competitive with the aldehyde
Ah, yeah, the aldehyde. Yeah, right. That's for example some unwanted product. And yeah, so if you know this potential energy surface, maybe you can get some idea how to steer the reaction towards the product that you want to have. Now, this potential energy surface, if you have a complicated reaction, it is, or I should say it differently. This is a two-dimensional example. And in reality, of course, you have many dimensions. Even in the example that Philip said with the isomerization, let's say we have, something like this in equilibrium with something like this. We have so many dimensions. We have the dimension of this distance here. We have the dimension, of course, the main dimension is this angle. That's the most important dimension. But we have also this angle here, which is important, and we have the other distance, which is important. And we have more than 5 or 6 dimensions that in principle we will have to look at. And that is normally not done. One restricts, one thinks, what is my reaction coordinate? Well, my reaction coordinate is this rotation coordinate. And then maybe I say, okay, that's one dimension. What's the next important one? And maybe the next important one is this distance or this angle here, because they will influence the energy that you need when you rotate around this central bond. And so maybe you end up with a 2 or 3 dimensional potential energy curve. And it's the same in physics. In physics, the people started to investigate these things with a very simple reaction. They just studied the reaction hydrogen molecule plus hydrogen becomes hydrogen atom plus hydrogen molecule. And if you look in the internet, you find many examples where these potential energy pictures are shown. Let me try to find it quickly. So if you just look H3 potential energy surface in Google and images, okay, then you see countless examples of the hydrogen reaction. And so you see that's exactly the same thing that we spoke about. And here are the dimensions, and that's the reaction. But that's the potential energy surface of the reaction. And so it's the same thing that we mentioned. The reaction does not really go from the left to the right or something. It goes maybe from some place here in a complicated way to here, and then it goes back, or it crosses over this barrier here, and then it goes out here, or it does nothing, it only goes here and never comes near the barrier. So this was historically the first reaction that was investigated in very much detail. So you have seen the collection of pictures that was there. They are all examples of exactly the thing that we showed you today.
I have another little example that is actually calculated. So I made, like Michael, I made some potential energy surface. I just guessed it or constructed it so it looks nice. And then I study that some particles can go over the barriers, or some systems can go over the barrier, and others cannot go over the barrier, even though the energy is the same. Minjay, do you have more?
No?
Okay, then
I mean, the next thing would be these analytical terms for the force field.
I see. Okay, well then I will just briefly show the other example so they really see the things moving.
And I give you the screen.
And I just reconstructed the old example, and I hope it will work. But sometimes it doesn't work on this other screen. I don't know why. It works nicely on my screen and not on the other. So something is different.
So in principle, you should not be afraid to look in Wikipedia. Wikipedia is very good for explaining all these things.
So I've written a little program. It's just a graphics program. And this graphics program, this shows a potential energy surface. And so this is the potential energy surface, 2 coordinates. I have just called X and Y. And here I have the contours, like I plotted before. And you see this has 2 transition states. So I have one minimum and I have another minimum. They are not equally deep in this case. And I can go from here to here through this transition state. And I can go from here to here through this transition state. So I have 2 transition states, and this one is lower than this one. So you see, there are 2 passages. There's a low passage going from here to here, and there's a high passage going from here to here. And now I can use a hypothetical particle as just a system to play with. So I say the mass is equal 1 and everything is equal 1, and I just solve Newton's equations. Right? So I take the potential energy surface, and I know that the force is just the derivative from the potential energy surface. So I can compute the derivative. I think I compute it numerically. And I start the particle. And when I start the particle, of course, I must say where is the particle? Where do I start? And what velocity does it have at the beginning? This is what is called the initial conditions for the differential equation. Okay, now let's start the particle. Well, not much has happened. And now you see it very, very weakly that the particle has moved. It has actually crossed the barrier. I mean, just first try, lucky, particle started here, went against the wall, back, and oh, lucky I hit the barrier and I'm on the other side. So this is a very lucky event. And here I've written some conditions, and the important is the energy is 2.1. Some units, I don't know what. This whole thing is done without units. Okay, and then I can continue the trajectory. So what will happen to the trajectory? Well, it will go on. So on and on and on and on and on and on, and you see, it stays mostly in the second well. It doesn't really go back. So somehow it's stuck in the second. Now suddenly it goes back. Okay, back and forth and back and forth and back and forth.
Let me choose a different path.
And at the end, you can use this 2D picture, which is easier to see where it went. Okay, and then we can start again. So we start again with the same energy, 2.1, but with different conditions. And we integrate, but again, lucky, it goes over the barrier and again forward and backward and forward and backward. So we have basically nicely equilibrium. And the equilibrium constant, of course, would be how often is it on one side and how often is it on the other side. You just count how often on one side of the barrier, how often. Okay, third try. Start. Rub. Same energy. Stuck. Never crosses the barrier. So this is unfavorable condition. The momentum is never correct to cross the barrier. Same energy. Okay, and I have more examples. I don't know what they do then. So when you do such studies, and many people do such studies, I mean, these studies are have been historically very, very important, for instance, to understand interstellar or to understand interstellar chemistry or to understand the chemistry in the atmosphere. Everybody talks about climate change and blah, 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 and blah, 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 and blah, blah, blah. Now, do you know who the pioneers, who were the first scientists who started doing studies like that so they could understand the reactions in the atmosphere? First one was about the ozone, that people said there's too much ozone or not enough ozone, and there is this ozone hole over the South Pole. And these people got a Nobel Prize. Do you know the names by it? Everybody is in environment, but who were the pioneers? No? Roland, Molina, and Crutzen? Never heard? Okay, so these people, they did such studies to determine the rate constants, because in the atmosphere they're very important, to determine the rate constants for reaction in the atmosphere. I mean, you know, what makes ozone? How long does it take to decay? Why are these chlorofluoromethanes so bad, and what do they do, and how slowly do they, and all that. This was done with studies like this, and you see that to get a realistic, a chemically important result, you must average many such crossing events, right? I mean, you cannot conclude the because you have one that stays on one side, you cannot conclude it will not react, right? Or if you have one like this, you cannot conclude it will react all the time. So this is done with statistics, and this is why it's called statistical mechanics. Okay, so it's the first time that we encounter this notion that in individual cases things are different. Sometimes we cross the barrier and sometimes we don't, and we have to average. Here's again one that remains stuck. I think maybe this one at the very end it crosses, I don't know, let's see. No, this never crosses. I don't know whether I have some examples at higher energy, so you can see at higher energy, it also goes over the second barrier. So you have a competition that sometimes it goes over the low barrier, but sometimes it also goes over the high barrier. And these studies in the literature, usually they are simply called trajectory studies. So you study the exact trajectory, including energy and including momentum of a particle or a pseudo-particle over a very complicated potential energy surface. So people say energy landscape. Energy landscape because you think like hiking in a mountain. Up the hill, down the hill, in the valley, and so forth. Okay? So an important thing to remember is if you do transition state theory and you look only at the energy, sometimes it's not enough. If your potential energy landscape is complicated, like you have several transition states and the reaction coordinates are very strange, curved and such, then you cannot look only at the energy. And actually, if you read a good book about transition state theory, they will tell you the assumption is that all degrees of freedom perpendicular to the transition state are at equilibrium, which means that you have sampled them enough. That's something like called RKKM or something blah blah Ruderman. I don't know. It's a field where there is lots and lots and lots of work. Okay, but everything relies on knowing the potential energy surface. If you don't know the potential energy surface, then you have lost. then you are dead.
So for the same system like this, sometimes it crosses, right? Sometimes it doesn't crosses. What is really the condition for this one?
I mean, to answer your question, I would need the notion of phase space, which we have not yet decided, not yet discussed. So of course, you can look at this so-called phase space, and then you can sort of try to find the part of phase space where the trajectories cross and the part of phase space where they do not. But most of the time it's not so easy. Most of the time people just make many tries like that. I mean, many means 10,000 or 100,000 or something like that. So you compute 100,000 cases, and then in, 85,000 it crosses, and in 15,000 it does not, and then you make statistics, you look at this. You do not really try to determine a priori which one will cross and which ones will not. But you could if you understand this notion of phase space. But maybe next week, well, I don't know. Maybe next week we discuss phase space, or in February. I don't know yet. Yes.
which one is correct part, and it's about the momentum. So the momentum is the vector. So is this depend on the term of the velocity of the main?
That's right. It depends on the velocity. See if.
Because the velocity is the vector, right?
I mean, let's look at the contours very close to the transition state. So I will look here only at the transitions. That's the wrong pen anyhow. Good that it didn't work. Good that it didn't work. Oh, it doesn't work either.
Click on.
Where is Noton? So let's look at the transition state. So the contours at the transition state maybe look like this. Okay, so here's the valley. So maybe the reactants are here, and here's the other valley, and maybe the products are here. Okay, now I am a system. Let's make it red. And I am here. Okay. Now, let's say this particle has some kinetic energy. So mv square is something. Okay. So I look at the kinetic energy of this particle at this time. So this particle that came up here, I don't know how. So at t equals 0, we are here. At some time t, we are here. And then we look at the velocity. So I plot v of t. Let's use again another color. So v of t can be like this, or the same v of t, the same magnitude, can be like this. So it has exactly the same energy, it has exactly the same kinetic energy. What is different is the direction of the velocity. And you see, if it comes like, if the velocity is like this, then it will probably manage to cross the barrier. Maybe not exactly at the minimum, maybe a little bit on the wall above the minimum, like a motorcycle that goes around the curve. But you see, if it has this velocity, it will just, I have to make more contours. So here, of course, there are other contours, so it goes up and up and up and up and up. And so if it has this velocity, it will just bump into, maybe it will come up to here, and it will go boing. It will stop here, I mean, it will have the velocity 0 here, and then it will just come back. It will not cross, it will come back, and it will go back into the valley. And you see, if you look here, you see many, many events where, it's hard to see. But if you look carefully, I can give you a little program if you want to play with it. You see many, many events where it just hit the ball. And if the contours here are like this, or if this hill here is quite flat, so it can go, or it has a good chance maybe to go a little bit higher here. But if the hill is very steep, if this saddle point is very narrow, then the velocity must really be exactly in the right direction, otherwise it always hits the wall. Now, some people in biology tell me that such things, some biologists think that such things having very narrow reaction or transition state is something important in protein folding. That there is really only one way the protein can fold, and all the other ways lead to too high potential energy, and the system goes back and tries again, and goes back and tries again, until it just finds. It's like going through a hole. Okay? So this is what happens here when we have trajectories that move forward and backward. It just means they never hit the hole. They never come to the transition state with the correct velocity. Like a drunk car driver who never manages to get the turn and always hits the tree.
Can the particle that have kind of like wrong momentum, can go to another side, because since like
if it has enough energy, I mean this one just does not have enough energy. But if it has enough energy, and this is, see here I said energy 2.1, maybe I can make some example where there's higher energy. Then it is quite possible, let's do it in the contour here. So let's say I start with high energy. I mean, this energy here, you see, is so high, I should easily be able to go over the transition state. But maybe, it rattles around, I don't know what, never really hits, and then suddenly goes over this transition state. That's possible. It has enough energy. Yeah?
It's in real life, scientists, they do something like this.
Yeah?
They prefer to change the landscape or just add more energy.
Well, the landscape, this is really determined by the reaction you want to study. So, if you want to study, I don't know, O2 plus O makes O3, which is this very important reaction in the atmosphere. This determines the potential energy surface. So, you do some quantum calculation, you ask him, and he makes a quantum calculation, and he changes the distances and the angles and everything, and makes a nice potential energy surface like this, and Michael will explain a little bit now how we do it mathematically. So the potential energy surface, this is really your problem. This is the molecule you want to study. And of course, this how your system moves in the potential energy surface. Well, this you really have to try. This you cannot determine because in the atmosphere, if you have O2 and O, well, you don't know whether they will come like this or whether they will come like this, or whether they will be fast and whether this one will be rotating or not or whatever. So this trying many things, this is like trying, many, coming fast, coming slow, coming like this, coming like that, rotating, not rotating, etc. So that is, in the atmosphere, you cannot know, I mean, the molecules in the atmosphere, they are not all like this or something. So you have to sample. You have to do all possibilities and make average of all possibilities. Okay? More questions? Okay, so now comes the question. I mean, I can make these drawings like this, but practically, what mathematical expression? What can you use to express this mathematically? I mean, this is of course some function, which I don't even know what it is. I would have to look up. But this is some function v of x and y. What is it? Is it polynomials, or is it Lennard-Jones, or is it Gauss function, or is it something? But you have to express it. I mean, you know, when I made the program, I had to tell the graphics program, please plot this and that function. Now here, this and that function, I guessed. But if you have a real molecule like O2 plus O, you cannot guess. I mean, you get the energies from him, but you get only the energies. And then, how do you express it? X squared plus Y squared plus XY plus cosine Y plus blah, blah. You don't know. And this is what Michael is going to talk about. And this is what we will discuss a lot also next year. This is what is called modeling. This is the real, when people talk about modeling, this is, we know the energy is now, let's write something for the potential energy surface. Okay, and one something we already know, this is this Lennard-Jones. We could, but you see Lennard-Jones is one-dimensional, so this is two-dimensional, and this has a barrier. I mean, Lennard-Jones doesn't make a barrier, so we need something else. Okay, and this will be the topic for the foreseeable future. Not this afternoon. This afternoon I will tell you something completely different, because it's Friday afternoon.
Yeah, but we will have our break soon, so let's start with this introduction that Philip mentioned, and I get my cable again.
Oh, sorry.
And so we have studied this potential energy surfaces, what is the meaning of some minima and transition state and so on, but we did not speak about how to write it down for real chemical systems. And that is what we must do now. And so, again, our slides, and just to link to the thing that we have discussed before, what was the important thing? The important thing was that minima are isomers. A minimum is isomer. That's like this nice example with the cis and trans. And they are different minima, reactants, products. They are connected via saddle points, and the saddle point in chemistry is called transition state. And yeah, mathematically you can find mathematically in real computer codes, transition states are found in the same way like a minimum. You do a minimization, but you minimize not all coordinates, because one coordinate you maximize. And we don't speak about the ways how to do it. And the difference between the energy of the reactants and the energy of the saddle point is the activation energy. And then we call also the lowest energy pathway, this red curve, normally we call it the reaction coordinate. But the question is always how to express the PES. That's the big question. It's a function of the coordinates of all atoms. And For small systems, you can really do it like we mentioned before, making a quantum chemical calculation, maybe with hyperchem or Gaussian, for all possible X, Y, Z combinations of the atoms. So that is the pointwise approach. But for complicated systems, that is too cumbersome. And so the people have invented some general rules how this BES can be written down for molecules and for ensembles of molecules.
You see, I mean, if you have a molecule and you have maybe you have some OH here and you have some OH here, then it's probably a good idea to say, well, the potential energy variation for this OH and for this OH is the same. So maybe I can find some like a Lego block for the potential energy surface, and every time I have some OH, I just use this block. So I use some sort of a standardized OH potential, or maybe a standardized CH potential, or a standardized what have you.
So that's just what I said already, you need it, you desperately need it, and it needs also to be possible to calculate the energy, not just hypothetically, but in practice you must be able to calculate quickly the energy if you have the coordinates. And quantum mechanically you can do that, but only for small systems. And one way of expressing the potential energy surface approximately is the so-called pair approximation. The pair approximation uses chemical knowledge. It uses the knowledge that normally this potential energy surface is not some function that jumps around wildly. If you change a little bit some coordinate, you get a completely different energy. No, this potential energy function is a rather smooth function. It is a very regular function normally. And so you can say, I assemble my energy from pairs of molecules and also pairs of atoms, but for atoms within the same molecule, you need to care about other things as well. And this whole thing is written down here as an example or as a sketch. So let's assume you have two molecules. They are just some maybe organic molecules. And how can we express the potential energy of these two molecules? So there's a part of the potential energy which is inside the molecules. That's the intramolecular interaction. Intramolecular interaction. So each molecule has its potential energy part. And then there is a second contribution. That's the potential energy between the molecules. And normally one treats them a little bit differently because that is just more practical. In principle, you would not need to care about the difference between atoms inside a molecule and outside. It is just something that you know from chemistry, that inside a molecule you have things that you have not between the molecules. And what do you have inside a molecule which contributes to the energy? Well, you have the energy that you need or that you get maybe if you change the distance between chemically bonded atoms out from some equilibrium value. So we say if the distance between maybe H and C is the lowest energy value, which is approximately 1 angstrom. If this distance is changed, maybe to 1.1 angstrom, you need energy. And so you can write down a formula for approximating the energy that you need if this distance is changed or is different from 1 angstrom.
So you see, you could write, if you are really crazy, you can write the potential energy as a function of x1, y1, z1, x2, y2, z2 when you have two particles. Okay? But you know that x1, y1, z1, x2, y2, z2 is not a good set of coordinates. Because you know physically the important one is the direction. The distance, I'm sorry, the distance. So the really important coordinate is square root of x1 minus x2 squared, so the distance. And of course, when you try to write down some mathematical expression, you will use the best possible coordinates. And this will be the distance. So you will write your function as a function of distance and maybe something else. Because it's much easier to write a function of a distance than to write a function of 6 x, y, and z. So the whole thing is to select what is important. So certainly the distance between two atoms, this will be very important in determining what the energy is. But if you want, absolutely, and you are really crazy, you can use other coordinates.
The thing is also that if you have Cartesian coordinates, it is very easy, like Philip has said, to calculate these internal coordinates from them. Distance is just the square root of the sum of the differences squared of x, y, z, and for the angles, as we will see, it's similar, and for other coordinates it's also similar. Now the question is, maybe it will be on the slides later, but I have just written it down. A simple possibility how one could say this is the energy which comes from the bond stretch. So we can say it's just the difference to the equilibrium distance squared and some scaling factor k, some scaling factor k that looks suspiciously like the spring force constant. And that will be not so very accurate maybe, because when you condense the distance, when you squeeze it, it will be a little bit different than if you make it longer. So if the R0 is 1.0, if it is CH 0 equal 1 angstrom, then 0.9 will be a little bit different from 1.1. The energy of 0.9 distance will be different from the energy at 1.1, but maybe not so much. So we can say it's a harmonic formula, it's a parabolic function. the energy is a parabolic function of the distance.
This is exactly what we did 2 days ago here.
And the K, of course, that is very specific. That's a K, a CHK. It will be different from the OHK or from the whatsoever K. So this energy terms, they contain normally equilibrium value and some scaling constant. And in the language of these modeling people, the collection of all the K's and all the equilibrium numbers is called a force field. So that's what the people call these tables of the equilibrium distances and the scaling constants. Okay, so that's nice, and we see we have many bond stretches. Some here, some here, some here. We have as many bond stretches as there are bonds, of course. And from chemical knowledge, we know that it really needs a lot of energy to make a bond longer or to squeeze a bond. But there is also a similar, a little bit smaller contribution to the energy, which comes from angles between three atoms. So I can leave that here. And that's symbolized here. Here is a group of three atoms. Maybe it is, I don't know what atoms it is. This will be carbon, and what is maybe chloride. Maybe it's carbon, chloride. Chloride has always this poisonous yellow color, so it's maybe chloride. And well, chloride should be bigger, I suppose, but I don't know. Anyhow, let's say it's carbon, chloride. And if I change this angle away from the equilibrium angle that it likes to have, I also need some energy. So I can write a similar formula here. I can say energy proportional to K CCCl times angle minus angle equilibrium, or I call it zero again. I call it zero square. And this is the CCCl equilibrium angle. And the K will be smaller, this K will be smaller than this K, because the angle is always a little bit more flexible than the distance. But of course that depends on your units also, if you how you measure it. And so we have considerably, if you count the angles, we have considerably more angles than distances in the molecule. And what else do we have, what we know from chemical knowledge? Well, let me delete this now. We have one more type of angle that's a little bit different from the bond angle. We have this so-called torsion angle. And the torsion angle is also called dihedral angle. And it's exactly the same angle that in the example that Philip gave you from the cis and trans isomer came up. That's a typical torsion angle, because you rotate around a bond. So you have some atoms on the left side of the bond and some atoms on the right side of the bond. And if you change the rotation around the bond, you have a different energy. So that's symbolized here That's a C torsion, C torsion angle. So torsion angle always involves at least 4 atoms. And now what would be a possible mathematical formula for the torsion angle? Well, the torsion angle has one speciality that is different from the distance and from the bond angle. That is, if you rotate it by 360 degrees, you come back to the original position of the atoms. And so you cannot use this square because, you know, that's a little bit similar to what Philip said, that in microscopic world you have no friction. It's also in microscopic world if you have a rod of steel and you rotate it by 360 degrees, then it has a you need how shall I say, you need some energy, and if you rotate it again by 360 degrees, you need even more energy. But for a molecule, if you rotate it by 720 degrees, you are back at 0, and nobody keeps track about the number of rotations that you have performed. So in the microscopic world, you cannot count this.
I mean, you cannot twist the bond. You cannot bonds do not behave like this.
So the electrons, they are not twisted.
No, you turn once, and then you're the same thing. I mean, see, my arm is not the same thing, but the molecule is the same thing.
And so, what is the maybe simplest possible mathematical expression that describes this periodicity of the torsion angle is some sine or cosine function. So one can say that the energy is proportional to the force constant again, or I call it scaling constant, and then some cosine of this torsion angle. Yeah, how shall I make a symbol of the torsion angle? I don't know. I just write TA minus TA equilibrium, or TA 0, TA C 0. And yeah, actually one could have some periodicity inside this cosine, which comes from the fact that sometimes you have not this 360 periodicity, but for example in a methyl group like here, you would have 120 degree periodicity, because if you rotate a methyl group by 120 degree, also the hydrogens are just replaced with each other, but the methyl group is indistinguishable from the original one. But we don't care so much about that now. Okay, so that is the torsion angle contribution to the potential energy. And of course you have also many torsion angles in your molecule. You could count them. There are many, because you have all the side atoms contribute to other torsion angles. So you have also, for example, you would have this torsion angle here.
So molecule symmetry also affect the energy of the torsion as well.
I mean, your potential energy surface or your expression that you use, they must reflect the molecular symmetry, of course.
Mm-hmm.
You know, if I have H2O, and if I select to write a bond, OH bond potential, that is a function of the OH distance, like Michael said, bond stretching, I must write the same. I cannot write two different potentials, because this OH and this OH, of course, is exactly the same.
Mm-hmm.
So if I select one OH potential in a symmetric molecule, I must use it for both parts. And as we shall discuss, or maybe you can think about it over lunch. So we will stop for lunch now, and we talk about VOH, for instance, potential for OH stretch. Okay? Now you know that hydrogen that also has isotopes, and the one isotope is deuterium, D. Question: is the VOH potential the same as the VOD potential, or is it different? You argue your case after lunch.
And just so that we are kind of a little bit complete before we convene, before we adjourn. These are the important intramolecular interactions. And for the interactions between the molecules, there are normally one takes into consideration two more terms. One term is just good for preventing the atoms of the two separate molecules to come too close to each other. And that could be symbolized here, so it could be very well a Lennard-Jones interaction potential. So that's something which is very easy to calculate, and it gives you just the interaction between non-bonded atoms. And I think you know the formula for the Lennard-Jones interaction. And then there's a second thing which is also playing maybe a little bit similar role in non-bonded atoms, between non-bonded atoms, because for bonded atoms you don't need it. And that is the electrostatic interaction. So you have a Coulomb interaction between these two atoms, for example. So that is the charge 1 times charge 2 divided by R. That is the Coulomb interaction. And yeah, then you can ask yourself, how can I know the Q's? And they are also part of this force field. So they are estimated in tables, and normally they are characteristic of the atom and sometimes of the atom in its chemical environment. The same thing goes, of course, for the Lennard-Jones parameters. They are also in the tables that are used by the computer codes. And I think that was all important for getting an idea how this intermolecular and intramolecular interactions can be written down so that you have at the end your potential energy surface. And the next slides, the next two slides, I will just go over them very quickly. Just repeat what I have said already. So you make a kind of distinction between bonded atoms and non-bonded atoms, because the bonds are always the strongest thing. Okay. For the non-bonded atoms, you have only two terms between the molecules, of course. The Lennard-Jones, here it's written van der Waals, but it's the Lennard-Jones, which is sometimes called van der Waals, and the electrostatic interactions. That's the formula of the Lennard-Jones. It's the thing that you know already. And the formula for the Coulomb is, of course, that one, which you know also, electrostatic formula. And this is a summary of the things that we mentioned when discussing the intramolecular interactions. So here you have bond distance change, which gives you some energy change. Here you have a bond angle change, which gives you some energy change. And here you have a torsion angle rotation, which gives you also a changing energy. That is just the same thing as before in one picture, nicely compressed. Okay, so that was what I wanted to say about this setting up, or typical setting up, or the simplest way of setting up a potential energy surface for a multi-atom system.
So you see, this what we're discussing now are your Lego stones. Which Lego stones do you have to build a mathematical expression that will reproduce your energies? So one building block is bond stretch, one building block, like written here, one building block is angle bend, one building block is torsion, one building block is to say I have two molecules, so each molecule has nucleus and has cloud, has electron density. So nucleus plus electron density here, nucleus plus electron density here. How can I describe this? Which Lego stone do I have to describe this? Well, the one that was on the slide before, van der Waals or Lennard-Jones, and then maybe Coulomb interaction. And the trick is now, I mean, this is full of coefficients. You see, you have this KB and K theta and K something, and these charges that appear in the Coulomb, and the A and B, or epsilon and sigma in the Lennard. All this you need to determine for a specific case. You know, you have some molecule here and a molecule there, and what are the epsilons, what are the sigmas, what are the k's, and all this needs to be determined before you can do anything. And you determine them very often by, you compare, you do quantum calculation, not for the whole big thing, but for some small blocks. I would take only this part, and I would compare with my Lego. Does the Lego describe it well or not? For instance, bond stretch, you know, you have to determine this, what is it called here, KB, and this you can easily do a quantum calculation where you change only one coordinate, like here. So quantum for many intermediate positions, and you compare that, and then you can determine KB for your bond stretching Lego stone. And this is the duty of modeling. This is what you really do when you do modeling. try to give a complete set, and the point is complete. We have to maybe next week think a little bit what this, how many like these do you need? And we have to think. Well, very very general. Just before we go for lunch, I have a molecule with n atoms. How many independent coordinates do I need to describe these n atoms? Okay, one atom. How many coordinates do I need? Three-dimensional space. 3. X, Y, Z.
Yeah.
Or if you use other coordinate system, if you use spherical, you know about spherical coordinates? Electric engineers know about spherical coordinates because you always solve Maxwell's equation in spherical coordinates. R, theta, phi, or some other coordinate. But you need 3. I mean, always 3 independent. If you have 2 atoms, how many coordinates? 6. N atoms, 3n. So this is 3n xyz, but as I said, it can be 3n any other independent coordinates. And here these bond stretches and angles and torsions and stuff, they are also coordinates, but sometimes they are not independent. But if they are independent, and again, you can make them independent, this is like this orthogonalization we talked about. Nobody does it, but you can do it. And actually they are called normal modes, these independent coordinates. You also need 3n. So in the best possible case, you need to find 3n stretches and bends and torsions, and then you have 3 translations, well, you don't really need, but you need 3 rotational coordinates, which usually do not change the energy, but they are there nevertheless. So just finding out, do I have enough coordinates, sometimes is not so easy. Because, you know, if you have 10 atomic molecules, you need 30 coordinates, where it's easy to overlook 1 or 2. This is the important thing to remember, that in an n particle problem you need 3n independent coordinates. X, Y, Z, Y, or R, theta, phi, or you can use cylindrical coordinates, or there are many other coordinate systems that you can use. And this coordinate system that Michael just described, the bend and stretch, and they are called internal coordinates. But they are not necessarily orthogonal. So we learn here that we can also work with non-orthogonal coordinates. Sometimes we must. Which means you need more. Okay? So, is it time for lunch? Oh yes. So, we meet again at 1 o'clock?
Or let's maybe say a quarter to 1, a quarter past 1.
A quarter past 1? Okay.
1 hour is necessary.
So we can have a more leisurely lunch?
for lunch.
Okay, so a quarter past 1. I will leave my stuff here.
Yeah, I have to charge my PC.
You have your charger?
No, I have it in the room, so
Oh, you have to go to the room.
I will go to the room.
Maybe you can use, I don't know.
No, that doesn't work.
Completely not standard.
Yeah, it's really non-standard. Now the new ones have USB-C.
Yeah.
Then I have to use
ใส่หน้า
it.
ไปแล้วแค่แบบผม
Okay.
สลัดโลนึง
So,
ไม่
see you later.
ดีอยู่เลย
แต่คุณต้องใช้อย่างน้อยอย่างน้อยๆไม่ว่าอินเทอร์แอคชั่นไหนก็ตามที่อยู่ในเฉยๆก็สามารถซึ่งผมว่าความดี
Can I have a some question
Yeah?
to make sure my understanding? You mean like when we
ผมจะวางอยู่ในสเปซเนี่ย
when
จะ
we
วางไว้ที่
consider their energy, we always have a t-dimension between one state, one base, or voltage point, right?
Well, I mean,
อ๋อ คือมันต้องเป็นระนาบเดียวกัน
ไม่จำ
the statement that you need 3 n coordinates for an n particle problem, this is very general.